Okay, hello everyone, and thank you for joining my talk today. I'm Wu Ming, and I'm here to present ArcNeural. This is a multi-modal database designed for the Gen AI era. And currently, I'm working with Fabata Inc., and ArcNeural is the product of Fabata Inc. I'm also working at the Hangzhou Dianzi University. And I will share the ArcNeural integrates various data models to meet the evolution demands for AI applications. Okay, here's the overview of what we will covering today. Okay, let's start by talking about the generative AI revolution, which has transformative impact on the technology landscape over the past few years. At the core of the revolution is the rise of generative AI models, particularly large language models like GPT, which are capable of producing human-like tests or codes, or generating images and much more. These models have dramatically changed the way we interact with the technology. We have opened up some new possibilities for AI-driven solutions. Industrial-wide effects have been profound. Gen AI is being applied in numerous industries, from AI-driven customer service chatbot to recommendation systems. And for example, some areas like finance, healthcare, and beyond. And in this new era, enterprise customers are facing a significant shift in how they manage and utilize their data. According to IDC, only 20% of enterprise data is structured, and some stored in database like MySQL or Oracle or graph databases. And some are stored in the CSV files, Excel files, and most of the data, about 80%, is either unstructured or semi-structured. This includes things like documents, emails, reports, and harder to manage, but contain a wealth of untapped insights. Another key challenge in the Gen AI era is the growing demand for real-time intelligence decision-making. Enterprises are increasingly tuning to AI-driven solutions to make critical decisions, whether in customer service, fraud detection, supply chain management, or even marketing. To support those needs, enterprises' real-time data processing capabilities. Decision-making is no longer just about analyzing data offline. It's about getting insights as event happens in real time. This has raised the bar of databases to be highly responsive and capable of handling real-time workflows. Beyond that, there is the issue of massive data volumes. And with the adoption of AI-driven intelligence, databases are not only handling more data, but more diverse data types and complex relationships. For example, the sales transactions, unstructured data from customer feedback, semi-structured data from API calls, they all need to be processed. And finally, the shift to data-driven intelligence means that enterprise needs databases that can go beyond classic storage and retrieval. They must support efficient processing and analyze these vast data sets, enabling faster, smarter decisions that can keep with the pace of the modern business. Okay, let's dive into the problem and the motivation. First, let's talk about the insufficiency in existing databases. The relational databases were designed for structured relational data, which means they are optimized for things like financial records, products, inventories, and other things. However, they may be, it becomes, when the new AI applications requires this database struggle to efficiently perform vector search or capture the complex relationships between diverse data points that we see many in the AI workflows. And some inefficiency in the RAG systems, the retrieval augment generation system that combine traditional information retrieval with large language models to generate more accurate response. This challenge here is that many RAG systems suffer from insufficient context retrieval, and the traditional databases they don't have the ability to index and retrieve information based on semantic search. And this is often very common to be dealing with AI-driven insights. And so we need a new type of database like ArcNeural that is tailored specifically for the unique need for AI applications to ensure that we can process retrieval data in a way aligned with the modern AI systems. Okay, let's look at several business scenarios we have met in the past year with multi-modal solutions just beyond the RAG are required. Okay, for example, for the first one, recommend tourist spots in Guangzhou. For this problem, you can just rely on the general LM capabilities. Any standard large language model is enough since it can generate a response based on the core knowledge in the pre-trained materials. And second, let's look at the company leave policy. Here you need local knowledge and RAG. This leave policy is an internal knowledge, so an RAG system is often necessary to pull specific information from the company's internal documents. And let's look at the compliance in some financial reporting. This problem requires structured data with RAG. Compliance involves filtering through structured data, such as regulations or financial records, while also using RAG to access relevant internal reports for more accurate decision making. And there are different requirements for different scenarios. For example, the analyze calls for the revenue decline and suggest action. This is a more complex scenario, requires large language models, agents, and some cooperate with some small specific AI models. You need to combine the insights from multiple models to generate detailed analyze and suggest actions. Okay, in all these cases, one key is to use the right combination of models and the database abilities. Okay, after the motivation in this section, we will explore the design of an ArcNeural and look at the system overview and some key components. Okay, now let's go over the ArcNeural design architecture with a focus on how its core components. The TP partition primary on the left part is responsible for the managing key functions like session managing, the cipher extension parser, and the optimizer. These components work together to pass the optimized queries for execution. A critical part here is the plan parallel executor, which breaks down the complex text into smaller pipelines that are processed in parallel. This helps improve performance by distributed computing workloads across multiple workers. ArcGraph engine and the ArcVector engine in the middle side. The ArcGraph engine handles graph processing and including managing the topology cache and the property cache. This ensures that graph data is quickly accessed with efficient memory mapping, partitioning, and updates. The ArcVector engine supports HNSW. That is for the vector search. And the graph HDAP part to the right side of the diagram, you will see the ArcNeural AP groups, which is designed to handle hybrid transactional and analytical process for graph data. It uses multiple AP nodes to distribute the workload related to the analytical algorithms and graph learning algorithms. Okay, this part is about the storage layer, the persistent layer. and it stores to ensure data consistency and most of the data is right in the write-ahead log, and the write-ahead log can ensure the change is logged before it is applied to the disks. And the checkpoint mechanism guarantees that even if a failure occurs, data can be recovered. That is commonly used. And in this diagram, you can see how the wall logs operates in coordinate with Raft for replication across multi-machines. And for the single node storage, ArcNeural uses RocksDB, a highly efficient embedded data system. And in the distributed setup, it uses the TiKV, which allows for scalable storage. And for some cloud-based environment, the ArcNeural provides AWS S3 or OSS for enterprise scalabilities. Okay, the MEM engine. MEM engine is used for handling graph topology and attribute data and attributes. The MEM engine stores both graph topology and attribute data as associated with them. This allows for fast randomly access for critical graph data, which is essential for AI applications. And one of the key features of a MEM engine is its ability to handle screwed vertex connectivities, which is common in graph database, where some supernodes are connected with many more nodes than others. And the basic idea of MEM engine is simple. For example, for some vertices with a very low degree, MEM engine uses a vector-like structure for fast, simple lookups. And for vertices with a very high degree, MEM engine switches to more structure like B-trees or hash tables to handle the load effectively. And the vector indexing part. ArcNeural employs a hierarchical navigatable small word known as HNSW indexing to manage vector data efficiently. On the top left, you will see the query language to build the vector index. And to optimize the local storage, mapped files are used for HNSW indexes. And also with the associated payloads data is stored in the RocksDB. When working with massive volume of vector data, CMD's acceleration delivers a 4-time performance boost for vector queries, which is critical in some AI workloads. On the right, ArcNeural supports top K attribute filtering, commonly used in the IG recall step to filter and rank results. The unified query interface allows for interaction between real-time transactions and deep analytical workloads. While query is received, the TP layer performs semantic analysis to determine whether the query requires real-time transactional operations or the AP part. For example, a query may start by identifying a subgraph and then run an algorithm like PageRank and on the results. On the right part, there is an example of the query. In the previous version, that means 1.0, in the previous version, to handle the mixed transactional and analytical workloads, they require to dump the data from the TP layer into the local files and then load it to the AP cluster. This process was slow. And to handle this dumping loading problem with insufficiency, we adopt Apache Arrow, a colonial data format, and by using this, both in the TP layer and the AP layer, it can eliminate the need for data restriction. So the images left down shows the time improvement by different, you can see the first version, the offline graph computing task, takes the longest time due to the heavy transfer and the processing overhead. And each tab without error shows major improvement, but still suffers from insufficiency. And the aperture error can achieve the best performance and reducing the overall latency. Okay, the third part we will cover an application that is we have done in the recent months. This application is about a criminal network operating in encrypted community platforms like Telegram. These platforms offering privacy and security, but has some become hubs for illegal activities. These plans are popular, and but some illegal online gamblings or other crimes can be happen on these platforms, and the ArcNeural's graph-based processing allows us to map out these criminal networks, and by identifying patterns in the communication, transaction, and the connection between the individuals, and can help the law enforcement to disrupt these activities. To effectively combat these criminal networks on these platforms, we leverage the power of graph analysis with the large language models. Graph analysis provide a natural way to map relationships with communication data. As shown in the first image, we can retrieve hidden connections between suspects by analyzing both individual and group chat data. This helps law enforcement visualize how suspects are linked and identify the central figures in the network. Criminal networks often operate across multiple platforms rather than only the Telegram. Then they use shared identifiers like phone number or email address or IP address. By leveraging a cross-platform analysis, we can identify these criminal networks by linking their activity across various communication platforms. The next powerful feature is behavior analysis. By examining interaction patterns, graph analysis can detect suspicious behaviors and political collaborations. For example, frequent short interaction or sudden change in communication pattern might signal some illegal activities. And association analysis. We use association analysis to pinpoint key individuals in the network, as seen in the second image. By analyzing linking between suspicious accounts, we can establish strong connections within the network. This helps to identify top-level organizers or central players in the operation. While the graph analytic is essential for mapping relationships and connections for these criminal networks, LLMs can play a critical role in enhancing this process by analyzing and summarizing communication data. Let's explore them. For example, the first is the content analysis. LLMs allow us to automatically analyze communication data. They can scan through the chat logs to flag some potential criminal activities. For example, it's discussion about illegal transactions, gun trading, or other suspicious behavior. This provides investigators with a clear picture of what's happening on the talk. And some key information. One of the most powerful capability of LLM is the ability to extract key information from the unstructured data in the communication logs. These extraction details can be used in tracking suspicious and gathering further evidence. And some is summarization. LLM can also summarize some evidence from the large data sets and highlighting the most important leads for the investigators to focus on. rather than going through thousands of lines of chat logs. And intelligent interaction. LLMs enable intelligent interaction with investigators, and investigators can query the model for specific insights, such as asking about connection between certain individuals or looking for some unusual activities. The LLM can help respond with relevant information and suggest further area for investigation, improve the efficiency and the investigation process. One approach to convert the natural language into graph queries through a text-to-cipher, which generates direct cipher queries from natural languages. A user asks an investigate question in plain text, for example, who are the collaborators of some given user ID? The system processes this text, identifies the appropriate graph traversal need, and map the question to the relevant graph feature. For this, a cipher query is generated to retrieve the answer from the ArcNeural databases, but there are some limitations due to this text-to-offer option. Text-to-offer often face some challenge with more complex reasoning or multi-step operation. Some cipher calls, such as saving calls, are not fully implemented in ArcNeural's architecture. So this makes the problem even harder. And we choose another way as an alternative for converting natural language into graph queries. This method we call the graph agent. It is basically import LLM agents by function call. First, the graph agent processes the user's natural language to understand what graph operations are required. For example, the user asks for collaboration of a specific individual. The agent knows it needs to find a connection between nodes. Next, the agent generates a step-by-step plan to accomplish this task. This would include 3 steps: retrieval relevant nodes, checking their connections, and counting the number of connections for a specific feature. Once the plan is created, the graph agent uses a series of API calls to interact with the graph and retrieve the needed data. And here are some APIs we have designed for the agent. And the left part is some part of the prompt we use in graph agent. But the graph agent way tends to have a slower performance comparing to the text-to-cipher way. This is because graph agent generates a detailed step-by-step execution plan and interacts with the graph multiple times during the process. Additionally, the intermediate data generated can be very large, making it a challenge for the next agent in the workflow to process efficiently. And it introduces more complexity due to the need for price coordination of multiple API calls. We have classified all the questions into 3 levels: the easy, the medium, and the hard. For the easy questions, text-to-cipher combines with the prompt engineering techniques can deliver relative good results. For the medium questions, we use the graph agent if the text-to-cipher did not work, and the graph agent can improve the accuracy for the medium questions. But for the hard questions, they remains a challenge, and the accuracy is not yet satisfied. Okay, there are some key lessons we have learned from the graph AI systems. First, graph-related questions are difficult for the LLMs. Even some SOTA LLMs as GPT-4, they also struggle to understand the complex graph structure and the application needs. To overcome this, we have learned it is better to break down the task into smaller and manageable steps for better results, rather than trying to get an answer from a single step. And a clear and structured workflow is essential. Data labeling, design a clear graph schema applying data algorithms, and meaningful features such as node degree or central metrics is crucial to enable more effective graph analysis. This groundwork sets the stage for LLMs to perform better. And some prompt engineering techniques such as chain of thought and few shot learnings, they are valuable. Breaking down reasoning steps into smaller steps and use these steps to help LLM to think more clearly. And by employing few-shot learning with highly related examples. For example, we can generate some example cases and example steps by the performant LLM, for example, GPT-4, and then use it as the teacher and the instruction to teach the relative goal ability LLMs such as Qianwen. That this will dramatically reduce the costs. And some other techniques like self-consistency, they can enhance robustness. LLMs can produce inconsistent results, and when dealing with some complex graph queries. To mitigate this, we have learned to generate multiple ways for the same question with different ways and use a self-consistency approach to ensure a more reliable outcome. And this will help to select the most consistent and correct answer. And in fact, it is not reliable wholly on LLMs to the absolute accuracy. This is a bit hard now for the graphs. And instead, use them to generate more insights and initial leads that help analysts to save time. And the value lies in the speeding up the whole progress rather than expecting perfect results. Okay, this concludes my slides. ArcNeural integrates structured, unstructured, and semi-structured data into a single platform. This platform combines vector search, graph-based HTAP, and LLM analyze for faster, smarter insights, scalable and flexible. And ArcNeural is ideal for use cases like fraud detection and real-time enterprise AIs. Okay, that is my slides, and do you have any questions?